Now that we know about SN2 and SN1 reactions, how do we figure out when we're going to have one mechanism and when we're going to have another mechanism? The way you figure that out is by evaluating four factors. You're going to look at the substrate, the nucleophile, the leaving group, and the solvent. Okay, so anytime you have a substrate that's undergoing nucleophilic displacement, be that SN2 or SN1 reaction, you're going to have a substrate. That substrate is going to have an R group that could be methyl, primary, secondary, or tertiary. So first we're going to look at the substrate, meaning its substitution. Then we're going to look at the nucleophile. What type of nucleophile is going to be used might tell us whether or not we have an SN2 or an SN1 reaction. Next we'll look at the leaving group. This won't really tell us whether or not we have an SN2 or an SN1, but it will tell us whether or not the reaction will be favorable at all. And then solvent can often give us information about whether SN2 or SN1 reaction will be preferred. Okay, so if we were to graph the rate as a function of substitution, remember for the SN2 reaction, as substitution increases, the rate goes down, right? Primary is faster than secondary. Secondary is much faster than tertiary. So we can say that methyl and primary favor SN2 reaction. So if you see a methyl halide or primary halide, then it's a good bet that's an SN2 reaction. If you see a tertiary halide, you can exclude SN2 reaction because we know those cannot undergo SN2 displacement. In this particular case, notice that as substitution increases, the rate of SN1 increases. So if we have a tertiary halide, like I said before, it can never be SN2, it must be an SN1 reaction. So if you have a tertiary substrate, you know right away it's an SN1 reaction. The only tricky one is secondary halides, because you can see they're in the middle of the pack for both. So secondary substrates can undergo SN2 or SN1. So that's when we'd have to look at other factors. When we're evaluating the substrate, I said previously that methyl and primary almost never undergo SN1. There are some primary halides that can undergo SN1 reactions, particularly benzylic halides and allylic halides. If you ask yourself why, then it might make sense to you why, because notice if this leaving group leaves, we generate the allyl cation, which is resonance stabilized. And because it's resonance stabilized, it's more stable than a primary carbocation would otherwise be. Remember, the stability of the carbocation determines the rate of an SN1 reaction. Similarly, if this halide leaves, we generate a benzylic carbocation, which will have 3 additional resonance structures. So this is an extremely stable primary carbocation which can undergo SN1 reaction. I also want you to keep in mind that sp2 hybridized carbons never undergo nucleophilic substitution reactions. This is called a vinyl halide. This is called an aryl halide. We'll never see SN2 or SN1 reactions of these compounds. Okay, so after you've evaluated the substrate, now you want to look at the nucleophile. The nucleophiles in this category tend to favor SN2 reaction. So if you see one of these types of nucleophiles, you want to think SN2 reaction. These are strong nucleophiles. Strong nucleophiles favor the SN2 reaction because the nucleophile is reactive enough to attack the carbon without the leaving group leaving first. The qualities of a good nucleophile is that it's either a strong base, like the thiolate ion, hydroxide, alkoxide, anything with a negative charge really. These are weak bases. The halogens are weak bases, right? But they're very polarizable. So as we go down in the periodic table, our nucleophiles get fluffier, and those fluffy nucleophiles the electron cloud can easily get polarized and get attracted to that partially positively charged carbon in our electrophile. Notice these are weak nucleophiles. They're neither strong bases nor particularly polarizable. They're in the second row of the periodic table. So weak nucleophiles are not polarizable. They're weak bases. These tend to favor SN1 reactions. Does that make sense? Yes, it does, because what happens in the SN1 reaction, right, is that we have a tertiary generally a tertiary halide. So this won't undergo nucleophilic attack by one of these strong nucleophiles. It's too sterically hindered, right? But if this leaves, then we can generate a much more activated electrophile. And now, even though these are weak bases, they'll be able to attack that very strong electrophile. So what we've done is increase the reactivity of the electrophile in the SN1 reaction, so now even weak nucleophiles can participate. Okay. As I mentioned before, the leaving group won't really determine whether or not we have an SN2 or an SN1 reaction, but it will determine whether a substitution reaction will happen at all. So what you want to know is that substitution will only happen if you have a good leaving group. And these are the only good leaving groups: iodide, bromide, chloride, not fluoride. Sulfonate leaving groups, we called those mesylate, tosylate, and triflate earlier. Water and alcohol can also be good leaving groups. Nothing else is a good leaving group, so if you see something that's a bad leaving group, it will not undergo either SN2 or SN1 reaction. Iodide is the weakest base, it's the most stable, it's the biggest, right? And so iodide, alkyl iodides, if we have the same substitution, will undergo the fastest substitution, followed by bromides, followed by chlorides, and fluorides won't undergo substitution reactions. The last thing, which is the most complicated to understand, is considering the solvent that's used in the reaction. Here we have an SN2 reaction of 1-bromobutane with the azide ion. This is an SN2 reaction, and notice that it's very significantly influenced by the solvent. So if we use this solvent called acetonitrile, the rate is 5,000 times faster than if we use methanol as a solvent. Why is that? Let's think about an explanation for that effect. Well, what we can do is break these solvents up into two different categories. The solvents listed in blue contain OH bonds, and the solvents listed in red do not contain OH bonds. These are called protic solvents to indicate the presence of bonds to hydrogen, oxygen-hydrogen bonds capable of hydrogen bonding. These are called aprotic. We'll look at these in more detail in the next slide. So you have to have a polar solvent in order to dissolve your reagents. But we can have polar protic solvents such as water, methanol, ethanol, ammonia, or acetic acid. These all possess OH bonds that are capable of hydrogen bonding, or NH bonds. Common polar aprotic solvents are DMSO, called dimethyl sulfoxide, acetone, and DMF. Notice in these solvents what you have is a partial negative here and a partial positive here. On each molecule you have a partial negative and a partial positive, partial negative, partial positive. But you don't have any OH or NH bonds, right? So if I'm trying to carry out a substitution reaction, then these solvents will solvate my reagents differently. For example, let's consider a polar protic solvent. If we add a nucleophile, let's say sodium iodide, it's going to dissociate into sodium ions and iodide ions, and the negatively charged part of the molecule can attract this positively charged and stabilize this positively charged sodium, and similarly the partially positively charged hydrogen can stabilize this negatively charged iodide. So polar protic solvents can stabilize anions and cations. Both of those energies are lowered, and what you have is a bunch of solvent molecules surrounding your nucleophile, which makes it bigger, which makes it a worse nucleophile, which slows down SN2 reactions, right? But if we think about polar aprotic solvents, and we use the same nucleophile like sodium iodide, right? Then the partial negative end of the oxygen can stabilize this positively charged sodium. But notice that the partial positively charged carbon is buried in the middle of the molecule, so these nucleophiles are unsolvated. They're not solvated, which means that they're more available to react. So nucleophiles are more nucleophilic in polar aprotic solvents because they're not solvated. Nucleophiles are less nucleophilic in polar protic solvents because they are solvated. So that means for an SN2 reaction, a polar aprotic solvent is favored. Let's consider an SN1 reaction, right? In an SN1 reaction, the rate determining step is going to be dissociation to form a leaving group and a carbocation, right? If we can stabilize the carbocation, we'll increase the rate of the SN1 reaction. But we just said that polar protic solvents can stabilize anions and cations. So the polar protic solvent stabilizes the cation and the anion. Stabilization of the cation, or solvation of the cation, lowers it in energy, which means that SN1 is faster in polar protic solvents. These cannot solvate anions, so we're not stabilizing the leaving group. So that means that the products are more stable in polar protic solvents than they are in polar aprotic. So SN1 is favored in polar protic solvents. To summarize, when you're looking at deciding between SN1 and SN2 reaction, you want to look at all four of these factors. You want to look at substrate, which is the most important. Less substitution favors SN2, more substitution favors SN1. Strong nucleophiles favor SN2, weak nucleophiles favor SN1, and in order to identify a strong nucleophile, you want to look for something that's polarizable or a strong base or both. Leaving group is going to be important just to tell us whether or not the reaction is going to go at all. Substitutions only happen with good leaving groups, which are always weak bases. These can be iodide, bromide, chloride, sulfonates, water, or an alcohol. And then look at the solvent. Aprotic favors SN2 reactions, protic favors SN1.